I measured the joint biomechanics using the encoders on the motors in the joints, then figured out torque using the current sensors, and power is just torque times speed. So here's the knee angle graph. This is 10 strides, what the angle looks like over each stride, and then ankle angle, what it looks like over each stride. Now you can see this sort of flat line here at the end, and that's because each amputee paused for a split second at the end of every time they took a step, just to kind of like wait and make sure that the prosthesis is going to hold them and support them. They have a little, like they're just used to having to give that split second to be able to trust the prosthesis. And so that's why you have the flat line. But since each stride is roughly 1 second, then this flat line is maybe 10%. So it's about 0.1 seconds. It's not super noticeable if you're not looking at the graph, if you're just seeing them climb in real life. And the respiratory gases look like this. So this first part here is they were sitting to just kind of get a resting baseline. How much energy does it take to keep them alive? Then they walked into the stairwell, climbed up the stairs. They climbed 3 flights. It was 79 stairs. That's this yellow part. And then they climbed back down, walked over to their seat and sat for another 3 minutes to end it. Calculated their energy based off the oxygen and carbon dioxide. And then, because most metabolic assessments are done at steady state, like on a treadmill or they're just walking or something, there actually were no metabolic studies of stair climbing done on amputees and no transient metabolic studies at all. So over here, like, well, you can see their metabolic power. Basically, they started breathing easy at the beginning, and then they were really panting by the time they got to the top. So I just had to come up with a way to analyze this. So I thought, well, this looks like a first order response. So let me take this, find the time constant, and predict what their steady state constant would be. So I predicted it there, you can see. So over the time frame that they climbed at their predicted steady state value, and then compare that to the measured value and see for climbing with the robot leg versus the regular prosthesis, how did those compare? Then I looked at their joint biomechanics, and you can see for all of these subjects, they get pretty decent biomechanics. So healthy is the gray smear, and then each of these subjects is a different color. You can see the knee angle looks really good. Now the knee torque, the peak of the torque comes a little bit late, and it's lower, and the power is lower. That's because the motors were just not strong enough to snap somebody upright as fast as their normal leg could. So that's why those peaks are a little bit lower and later, because the motor's not as strong and it moves a little slower than their healthy leg. And same thing for the ankle. The ankle motor, you can see it dips down to push them off. It just can't dip as far and push off as fast as a healthy person can. So that's why the power peaks are lower. And then you can see here that it lifts back up at the end of strides so that the toe will clear the stair in front of them. The ascent times, we got some really great results for, and they all climbed faster using the powered prosthesis. You can see green is powered, blue is passive. So it was about 30% faster on average to climb with the robot leg than with their regular prosthesis. Similarly, for energy, it took less energy, both steady state and transient. It got very similar results. I think it was about 26% easier or less energy consumed to climb with a powered leg versus their passive prosthesis. And then I compared it to healthy people to see if the data was reasonable. So I took my predicted steady state, and then I found a study of healthy people climbing at steady state. they climbed 11 flights of stairs instead of 3. So they had time to get to steady state. And it looked like I was pretty near the healthy range. So my approximations seemed to be reasonable. The amputees thought the robot leg was pretty good. So you can see some of their testimonials here. They all thought that the prosthesis was good for making them like use less energy. It was easier to walk, to climb. It'll save their good legs so that they have just half as much stress on their good leg because now the robot leg is actually working for them too. So in conclusion, power prosthesis can make ascending stairs easier and more natural for transfemoral amputees. It was faster, it took less energy, and the biomechanics were infinitely better because the passive prosthesis doesn't really move at all. The National Science Foundation supported the research done in this study.